Hello friends. So, welcome to lecture series on matrix analysis with applications. So, in today's lecture we will focus on Cayley-Hamilton theorem and minimal polynomial, that what Cayley-Hamilton theorem is and how can you find the minimal polynomial using characteristic polynomial. So, what Cayley-Hamilton theorem states, let us see. Cayley-Hamilton theorem states that every matrix A, every square matrix A is a root of its characteristic polynomial. Okay. So, what does it mean? Let us see. We know that Ax is equal to lambda x. We already discussed this thing, that where x is not equal to 0 and lambda is a corresponding eigenvalue. I mean, if lambda is a corresponding an eigenvalue, then the corresponding eigenvector is x. Okay. So, lambda is a eigenvalue and x is the corresponding eigenvector. This we have already discussed when we are discussing eigenvalues and eigenvectors. Now, from this we can easily see that A minus lambda I times x equal to 0. Okay. Now, since x is not equal to 0, so this system of linear equations has infinitely many solutions. It is something like Bx equal to 0, where x is not equal to 0. See, for this system of linear equations where B is a matrix of order n cross n, this system of equation, if x is not equal to 0, means have infinitely many solutions, and this will be having infinitely many solutions only when determinant of B is equal to 0. So, here instead of B we are having A minus lambda I. So, this means since x is not equal to 0, this means determinant of A minus lambda I is equal to 0. So, this means this expression determinant of A minus lambda I equal to 0 gives a polynomial in lambda, and that polynomial in lambda is called characteristic polynomial. And what is the degree of that polynomial? The degree of that polynomial is the order of the matrix. Here I am taking order of matrix as n cross n. So, the degree of the polynomial of this will be simply of order n. So, suppose a polynomial which we are getting after opening this determinant is lambda raised to power n minus C1 lambda raised to power n minus 1 plus C2 lambda raised to power n minus 2 and so on, plus minus 1 raised to power n Cn is equal to 0. Okay. So, this polynomial lambda, this polynomial is called characteristic polynomial. Okay. So, how many roots this equation is having? This equation is having n number of roots. Suppose the roots are lambda 1, lambda 2 up to lambda n. Roots may be distinct, roots may be real, roots may be complex. Okay. Some roots are equal, some are distinct, anything. Now, we have already discussed that sum of the eigenvalues is equal to trace of the matrix. Trace means sum of diagonal elements, that is sum of over I, sum of AII, A11 plus A22 plus A33 up to ANN, okay, and I is varying from 1 to n. And this also we have discussed that product of eigenvalues is nothing but determinant of A. Okay. Now, Cayley-Hamilton theorem states that for if this is a characteristic polynomial of a matrix A, okay, then my matrix always satisfies characteristic polynomial. That means if for a matrix A of order n cross n, the characteristic polynomial is determinant A minus lambda I is equal to 0, which is equal to suppose lambda raised to power n minus C1 lambda raised to power n minus 1 C2 lambda raised to power n minus 2 and so on, plus minus 1 raised to power n Cn is equal to 0, then by Cayley-Hamilton theorem A raised to power n minus C1 A raised to power n minus 1 plus C2 A raised to power n minus 2 and so on, plus minus 1 raised to power n Cn into identity should be 0, should be a 0 matrix or a null matrix. That means, if you have a characteristic polynomial corresponding to a matrix A, it always be satisfied by the matrix itself. That is the main statement of Cayley-Hamilton theorem. Now, how can we prove it? How can we prove that a matrix whose characteristic polynomial is given by suppose this expression, it will be satisfied by the matrix also. So, let us try to prove this result, the proof of the Cayley-Hamilton theorem. You see, in order to prove, let us find adjoint of A minus lambda I. Let us find adjoint of A minus lambda I. You see, what is A matrix? Suppose A matrix is A11, A12 and so on up to A1n, A21, A22 and so on up to A2n, an1 and so on up to ann. This is n cross n matrix A. And what is A minus lambda I? A minus lambda I will be A11 minus lambda, A12 and so on A1n, A21, A22 minus lambda and so on A2n, and here an1, an2 and so on up to ann minus lambda. This is A minus lambda I. Now, if we want to find out adjoint of this matrix A minus lambda I, so how we will proceed? We first find cofactors of each element, take the transpose of the matrix found by the cofactors, that will be the adjoint of that matrix. If suppose we want to find out the cofactor of this matrix, this element, the first element, we want to find out cofactor of this element, we leave this column, we leave this row, and the determinant of n minus 1 cross n minus 1 matrix will be the cofactor corresponding to first element. Similarly, if you want to find out cofactor of A12 element, say for example, then you leave this column and you leave this row and you find out the cofactor of determinant of the remaining matrix will be the cofactor of that particular element. With of course, cofactor of Cij is minus 1 raised to power I plus j, minor of Ij, that we already know. So what does it mean? It means that if you want to find out the cofactor of any element of this matrix, say first element, so it will be the highest power of lambda will be lambda raised to power n minus 1. You see, if you see cofactor of this element, then the determinant of this will contain lambda raised to power n minus 1, not lambda raised to power n. If you want to find cofactor of this element, then the highest power of lambda will be lambda raised to power n minus 2. Okay. So, if you find cofactors of each and every element of this matrix, so this will be something like you can say that it is B1 lambda raised to power n minus 1 plus B2 lambda raised to power n minus 2 and so on up to Bn. Okay. This B1, B2 up to Bn, they are the matrices itself. Okay. They are itself the matrices. They are here B1, B2 and so on up to Bn are the matrices. Okay. Because when you write the determinant of this matrix, you open it, it will contain lambda raised to power n minus 1 and the other terms. Similarly, when you take the cofactors of other element and so on, so you will get lambda raised to power n minus 1 a matrix B1. Similarly, lambda raised to power n minus 2 a matrix B2 and so on up to Bn. You can easily verify this result by taking a 3 cross 3 matrix. So, you will find that B1, B2 up to Bn, in that case are the matrices of order n cross n, okay, of order n cross n. Now, we know that we also know that A minus lambda I into adjoint of A minus lambda I, that means A into adjoint of A. We already know it is equal to determinant of A times identity. Okay. So, this is matrix into adjoint of the matrix is equal to determinant of A minus lambda I into I. This we already know. So, you substitute this expression over here. So, what you will get? What we will get? You see, we are having A minus lambda I into adjoint of A minus lambda I. We are taking it as equal to determinant of A minus lambda I times identity. This implies A minus lambda I This is, we are assuming it is equals to b1 lambda raised to power n minus 1, b2 raised to power n minus 2 and so on up to bn is equals to determinant of, now determinant of a minus lambda I is we already know that it is lambda raised to power n minus c1 lambda raised to power n minus 1 and so on up to minus 1 raised to power n into Cn times identity. This we have already assumed that the determinant of this matrix is lambda raised to power n minus C1 lambda raised to power n minus 1 and so on minus 1 raised to power n Cn times identity. Now, let us compare the coefficient from both the sides. You see, what is the coefficient of lambda raised to power n? From here and here, when you multiply these two brackets, then lambda raised to power n will be minus b1 from this into this itself, okay, and that must be equal to I from here. Now, lambda raised to power n minus 1, lambda raised to power n minus 1, when you multiply this with this element, so it is a b1 and this with this, I mean this element with the second element of this bracket, that is minus of b2, that will be equal to lambda raised to power n minus 2 from here C1 times identity. Similarly, if you take the lambda raised to power 0 from here, so lambda raised to power 0 will be this into this, that is bn into a from here and no other term, and that will be equal to minus 1 raised to power n Cn times identity. Now, you multiply the first equation by a raised to power n, the second equation by a raised to power n minus 1, the last equation with identity, and you add them. When you multiply this by a raised to power n, multiply this by a raised to power n minus 1, then it will become a into a raised to power n minus 1 will become a raised to power n into b1. So, these two will cancel out. Now, similarly, when you multiply b2 with this element, this will be minus a raised to power n minus 1 into b2, which will be cancelled from the next expression, term in the next expression, and similar last expression will be cancelled from the second last one. Okay. So, when you add them, we obtain a raised to power n minus C1 a raised to power n minus 1 plus C2 a raised to power n minus 2 and so on plus minus 1 raised to power n Cn times identity will be equal to 0. So, hence we have obtained this result, which states that, I mean which tells us that characteristic polynomial will be satisfied by the matrix itself. So, hence we got the proof of the Cayley-Hamilton theorem. So, suppose we are having this problem now, matrix A. For simplicity, we have taken an example of 2 cross 2. Similarly, we can go for 3 cross 3 or higher orders. Now, let us suppose A is this matrix. Okay, we have to verify Cayley-Hamilton theorem and hence find A inverse adjoint of A and A raised to power 6. Now, what is A here? A is, you see, A is 2 minus 2 minus 2 and 5. First, we will find out the characteristic polynomial of this matrix A, and from there we will try to verify Cayley-Hamilton theorem. So, what is the characteristic polynomial? Determinant of A minus lambda I is equal to 0 is a characteristic polynomial. So, this implies determinant of 2 minus lambda minus 2 minus 2 5 minus lambda, determinant should be 0. So, this implies 2 minus lambda into 5 minus lambda minus 4 should be 0. This implies lambda square, this is minus 7 lambda plus 10 minus 4 is plus 10 minus 4 is plus 6 equal to 0. So, this is the characteristic polynomial of this matrix A. Now, what from Cayley-Hamilton theorem? From Cayley-Hamilton theorem, we must have A square minus 7A plus 6I should be 0. This we have to verify. In order to verify, you simply take left hand side is A square minus 7A plus 6I, and we have to show that it is equal to null matrix. So, first find A square. What is A square? A square is 2 minus 2 minus 2 5 into A itself 2 minus 2 minus 2 5 When you multiply these two, this row, this column, it is 4 plus 4 is 8. This row, this column, minus 4 minus 10 minus 14. This row, this column, minus 4 minus 10 minus 14. This row, this column is 4 plus 10 is 14. Now, now let us try to find this expression a square minus 7a plus 6I, which is 8 minus 14 minus 14 14 minus 7 times a. You multiply this with 7, so it will be 14 minus 14 minus 14, 7 5 is it is 35, 7 into 5 is 35 plus 6I, that is 6006. Now 8 plus 6 is 14 and 14 minus 14 is 0. Similarly, minus 14 and plus 14 is 0, minus 14 plus 14 is 0, and it is 14 plus 6, 14 plus 6 is 20. So, let us again verify this thing. It is this row, this column, that is 4 plus 25. Okay. So, here we have a doubt, here is a correction. You see this element, it is 4, this row, this column, that is 4 plus 25 is 29. Okay. So, this element is 29. Now, 29 plus 6 is 35 and 35 minus 35 is 0. So, it is 0 0 0 0. So, it is a null matrix 0. Okay. So, hence this Cayley-Hamilton theorem is verified. Now, we have to find out inverse of A using Cayley-Hamilton theorem. So, how we will find that? So, for this matrix we have seen that A square minus 7A plus 6I is equal to 0. This we have obtained by Cayley-Hamilton theorem. Now, what is the determinant of the matrix? Determinant of the matrix is simply product of eigenvalues, and product of eigenvalues is simply given by the last term upon first term, that is 6, that is the determinant. So, determinant is not equal to 0, this means inverse exists. First we have to get the insurety that inverse exists, and for inverse to exist, matrix must be invertible, I mean non-singular. For that, determinant must be non-zero, and from here the product of eigenvalue is 6. So, we can say that determinant is not equal to 0. So, A inverse exists. Now, how to find A inverse? Now, since A inverse exists and A satisfies this equation by Cayley-Hamilton theorem, so we can multiply both the sides, or we can operate both the sides by A inverse. So, let us operate both the sides by A inverse. It is 0. A inverse into A square is A minus 7 times identity plus 6 times A inverse should be 0. Now, this implies A inverse will be, you can put all the other terms on left hand side, it is 7I minus A. Okay. Now, what is A? A is given to us as, it is 2 minus 2 minus 2 5. So, what is 7I minus A? 7I minus A will be 7007 minus A. A is 2 minus 2 minus 2 5, and this will be 5 to 0 plus 2 is 2, it is again 2, as 7 minus 2 is 2. So, this A inverse will be 1/6 of this matrix, that is 5 2 2 2. So, this will be the inverse of this matrix. Now, next is we have to find out adjoint of A. Now, we know that A inverse is adjoint of A upon determinant of A. So, this implies adjoint of A will be A inverse times determinant of A. Now, determinant of A is 6, that we have already shown. So, it is 6 into A inverse, and A inverse is this expression. So, 6 will cancel out. So, adjoint of this matrix will be simply this matrix. Now, next we have to find out A raised to power 6 for the same problem. Okay. Now, by Cayley-Hamilton theorem, the characteristic polynomial is this. Okay. A square minus 7I plus 6I equal to 0, and we have to find A raised to power 6. So, it is very easy to find out using this expression. You see, A square is 7A minus 6I. You can find A cube by multiplying both sides by A. it is 7a square minus 6a, 7 times. Now, a square again you substitute this value, it is 7a minus 6I minus 6a, it is equal to now 42 minus 6, 42 minus 6 is 36a minus 42I, okay. Okay, it is 49, it is 49 minus 6, okay. So, it is 49 minus 6 is 43, it is 43a minus 42I. Similarly, you can now multiply, again you can multiply by a both the sides. So, it is a raised to power 4, 43a square minus 42a. So, 43a square is again 7a minus 6I from this expression minus 42a. You can simplify this, and again you can multiply by a raised to power 5, I mean a both the sides, and substitute a square from this expression, and finally a raised to power 6. Okay. So, finally you will get a expression of a raised to power 6 of this form, some alpha raised to power a plus beta raised to power I. Some expression of this form where alpha and beta can be computed by the successive computation. Then you can substitute a, because you know the value matrix A and the identity you already know, you can easily find out a raised to power 6. Okay. And the other way out is you can using Cayley-Hamilton theorem, it is like you might be seeing that for a 2 cross 2 matrix, either you can multiply a by 6 times, a square, then a cube, then a raised to power 4, a raised to power 5, and then a raised to power 6. But if it is a larger matrix of order say 10 cross 10, then finding a raised to power 6 is a difficult task. So, but by the Cayley-Hamilton theorem, using Cayley-Hamilton theorem, it is easy to find out. So, this is the main importance of Cayley-Hamilton theorem, to find out the higher powers of A, to find out A inverse, adjoint of A, and other things about the matrix A. Now, what is monic polynomial? A polynomial fx given by fx equals to a raised to power a n x raised to power n plus a n minus 1 x raised to power n minus 1 and so on up to a naught is said to be monic if the leading coefficient is 1. If this leading coefficient, which is a coefficient of highest power of this polynomial, is 1, then this polynomial is called monic polynomial. Okay. Now, what do you mean by minimal polynomial? Let T be a linear operator on a finite dimensional vector space V, then there exists a unique monic polynomial of minimum degree mt x such that mttv equal to 0 for all v in V. Then this mtv is called minimal polynomial of T. So, what does it mean basically? Suppose A is a matrix of order say 4 cross 4, okay, and its characteristic polynomial is suppose lambda minus 1 whole square, lambda minus 2, lambda minus 3. Of course, if it is of order 4 cross 4, so the degree of the characteristic polynomial will be 4. So, it will be having 4 roots. Suppose all the 4 roots are real. So, roots of characteristic roots are, or the eigenvalues of this matrix are, suppose 1 1 2 3. So, what is the characteristic polynomial? This is a characteristic polynomial of this matrix A, and by the Cayley-Hamilton theorem we can easily say that A minus I whole square into A minus 2I into A minus 3I, this should be 0, because by the Cayley-Hamilton theorem matrix satisfies characteristic polynomial. So, hence this will also be equal to 0. Now, minimal polynomial is the lowest degree polynomial for which is to be satisfied by the matrix itself. You see, what is the degree of this polynomial? Degree of polynomial is 4. Okay. The important property of minimal polynomial is it contains all the different roots. Okay. It contains all the different roots. The different roots are 1, 2 and 3. So, minimal polynomial will always contain lambda minus 1, lambda minus 2 and lambda minus 3 at least. Okay. All the irreducible roots it will be having. the minimal polynomial. So, either it is this polynomial which is a lowest degree polynomial, which may be the lowest degree polynomial and A is be satisfied in this expression, or it will be characteristic polynomial itself. I mean, I want to say that matrix A will be satisfied by either this or this. For this it is obviously true, because by the Cayley-Manton theorem, but we need a polynomial which is of lowest degree. So, it may be this polynomial also. So, for this polynomial we have to check whether A is satisfying this expression or not. If A is satisfying this expression, so this will be the minimal polynomial, otherwise this is the minimal polynomial, which is of course be satisfied by A by the Cayley-Manton theorem. Okay. So, minimal polynomial has an important property. Number 1, it is of lowest degree polynomial which is satisfied by the matrix itself. It contains all the irreducible factors, all the linear factors which the characteristic polynomial is having. Okay. Now, suppose you want to find out a minimal polynomial corresponding to a matrix A, how we will proceed. So, let us discuss it by an example. Suppose you are having the first problem 2 0 0 2, 2 0 0 2. So, what is the characteristic polynomial of this matrix? This, which means determinant 2 minus lambda 0 0 2 minus lambda should be 0, or it implies 2 minus lambda whole square is equal to 0. So, this is the characteristic polynomial of this matrix A. How many roots it is having? Only 2 roots, both are equal, lambda equal to 2, 2. Okay. Now, the minimal polynomial is a lowest degree polynomial, contains all the irreducible roots, all the linear roots, all the different roots, distinct roots. Okay. So, that means the minimal polynomial will be either 2 minus lambda or 2 minus lambda square. It is either having 2 minus lambda or itself. This will be always satisfied by the matrix itself, by the Cayley-Manton theorem. So, we have to check whether this is be satisfied by the matrix or not. If it is satisfied by the matrix, that means it is a minimal polynomial. So, this means we have to check that 2i minus a should be 0 or it is not 0. Let us see. So, 2i is 2 0 0 2 and a is simply of course the same thing. So, it is comes out to be a null matrix. That means this expression satisfying by the matrix A, that means the minimal polynomial of for this matrix is 2 minus lambda. Okay. It is of degree 1, not 2. So, the minimal polynomial of this matrix is 2 minus lambda. Now, let us take the second example to see whether it is what is the minimal polynomial of this. So, second example is, you see A here is 3 1 0 0 3 0 0 0 4. It is the upper triangular matrix, you can easily see upper triangular matrix, and in case of upper triangular matrix, eigenvalues are simply the diagonal elements. So, what are eigenvalues of this matrix? These are 3 3 and 4. And if you know the eigenvalues, you can simply find out this characteristic polynomial, which is lambda minus 3 whole square into lambda minus 4, that is that we can easily see. So, characteristic polynomial of this matrix A will be nothing but lambda minus 3 whole square into lambda minus 4. Now, we have to see what is the minimal polynomial of this matrix A. So, to see the minimal polynomial of this matrix A, minimal polynomial is lowest degree polynomial which is satisfied by the matrix itself. So, either it is, so minimal polynomial of this matrix is either lambda minus 3 into lambda minus 4 or lambda minus 3 whole square into lambda minus 4, because it contain all the different roots, all the distinct roots. all the factors having distinct roots. So, this is obviously satisfied because by the Cayley-Hamilton theorem. Let us see whether it is satisfied or not. If it is satisfied, then this will be the minimal polynomial of this matrix A. So, we have to see basically that A minus 3i into A minus 4i. What is the expression this? Let us see. What is A minus 3i? It is 0, 1, 0. It is 0, 0, 0, 0, 0, 4. And what is A minus 4i? It is A minus 3i is 0, 1, 0, 0, 0, 1, 0, 0, 0 and 0, 0, 1. Okay. Because you are multiplying this, you are subtracting 3 with each tiny elements. Now, A minus 4i will be minus 1, minus 1, 1, 0, 0, minus 1, 0, 0, 0, 0. Now, what is the product of these two? You multiply this with this 0, you multiply this with this is minus 1. If one element is non-zero, if one element comes out to be non-zero, this means it is not equal to a null matrix. And if it is not equal to null matrix, that means this can't be the minimal polynomial. So, what is the minimal polynomial then? The minimal polynomial will be this expression. This will be the minimal polynomial of this. So, in this way we can find out the minimal polynomial of a matrix A. Okay. So, basically if I am having a matrix A of order say 5 cross 5 and the characteristic polynomial is suppose lambda minus 1 whole raised to power 3 into lambda minus 2 into lambda plus 3 suppose is equal to 0, then the minimal polynomial of this I mean for this matrix A corresponding to this characteristic polynomial may be. So, what are the cases we have to check? For minimal polynomial we have to check this product whether it is 0 or not, this product whether it is 0 or not, and this product. This is of course 0 by the Cayley-Hamilton theorem. So, if these two are not equal to 0, so the matrix characteristic polynomial itself is a minimal polynomial. Okay. But we have to check for these two also whether these are 0 or not. Okay. So, first we will check for this, if it is equal to 0, so this is the least lowest degree polynomial which is satisfied by the matrix, otherwise we check for this. If these two are not equal to 0, then the characteristic polynomial itself will be the minimal polynomial. Okay. So, what are properties of minimal polynomial? The minimal polynomial MT of a matrix A divides every polynomial that has A as a 0, that is MT divides the characteristic polynomial of A. So, always minimal polynomial divides its characteristic polynomial. Okay. Number 2, it has the characteristic polynomial, the minimal polynomial of matrix A has the same irreducible factors which we have discussed. And number 3, a scalar lambda is the eigenvalue of a matrix A if and only if lambda is the root of a minimal polynomial of A also. So, if lambda is the eigenvalue, it is always a root of minimal polynomial also. So, these are some of the important properties of minimal polynomial. So, in this lecture we have seen that how we can find out characteristic polynomial, I mean how we can see and see the advantage or the applications of Cayley-Hamilton theorem. How can you find out minimal polynomial corresponding to a matrix A? Okay. In the next few lectures, we will see some of the important properties of or important advantage of minimal polynomial. So, thank you.